Good morning, AP Chem. Today we're going to be going over Unit 6.7, which has to do with more about bond enthalpies, and specifically calculating the change in enthalpy with average bond enthalpies that are involved. So we learned how to find delta H through calorimetry experiments in 6.4 and 6.6. Today we're going to figure out how to calculate delta H using average bond enthalpies, as stated in that second bullet point there. In many cases, this is the least accurate method for calculating delta H, and this is because it doesn't really take into account the different phases of an element or compound. So it assumes that water gas, water liquid, and water solid all have the same bond energies, which isn't necessarily true, but it's still good for educational purposes because it shows how endothermic and exothermic aspects of a reaction combine to give the change in enthalpy for an entire reaction. So with bond energy, the potential energy decreases as attractions between nuclei and valence electrons pull the nuclei closer together. So the energy that is lost releases heat during the formation of a bond, and the energy lost during the formation of the bond is equal to the energy required to break the bond. So remember that bond length at 0.074 nanometers, the bond length of H2, two hydrogen atoms, the potential energy associated with that bond is at its lowest point. This is how H2 exists on average, but remember that the bond fluctuates. It's not just stationary and stable, so there is some movement there. So we talked about like bond length and how when it's at the lowest potential energy, that's usually where the bond exists. So that was a few units back. When the bond length gets shorter than that average bond length, it's compressed and the potential energy rises because you're pushing those two nuclei closer together. So that increases the repulsion, which then would push the nuclei back apart. So energy is always released when a bond is formed. Potential energy decreases as the atoms move close together, and the same amount of energy must be added to break that bond for any given substance. So remember, in biology, it gets kind of confusing, especially with ATP. We talk about how breaking bonds releases energy that our body reuses, but that's not necessarily what is actually happening. That's a good summary. So remember, when you form a bond, you're always going to be releasing energy. When you break a bond, you always have to input energy in terms of chemistry. So during a chemical reaction, bonds are broken and formed, and this changes the potential energy of the system throughout. So in this diagram here, going from 1, this bonded molecule, to 2, which is 2 separate atoms, the amount of energy that's absorbed when breaking this bond is equal to the amount of energy that would be released when we form the bond. Okay, so equal but opposite in direction, just depends on if we're inputting energy or releasing energy. This formula, the delta H equals the sum of bonds broken minus the sum of the bond enthalpy of bonds formed. This is not given on the AP exam, so you always have to remember broken minus formed to calculate for delta H. So for an exothermic process, the average energy required to break the bonds of the reactants can be estimated by adding up the bond energies for the bonds in reactant molecules. And then the average energy released during the formation of bonds and products can be estimated by adding up bond energies for the bonds in the product molecules. So if energy released is greater than the energy required to break, then the process is exothermic because overall it is releasing energy. Whereas during endothermic processes, if the energy required to break bonds is greater than the energy released, then the process takes energy and it's endothermic. So energy has to be input into the system overall. So that's the difference really that we see between endothermic and exothermic. Of course, for endothermic, we would have a positive delta H because energy is taken in, and for exothermic, we would have negative delta H. So again, for endothermic, where it's positive, the energy required to break bonds is greater than the energy released when bonds are formed. So here we have a practice example. Calculate the enthalpy change for the reaction using the table of values. So here we have methane and O2 yielding CO2 and 2H2O. So the combustion basically of methane here. And sometimes I find that it's helpful to kind of draw Lewis structures. That way, we don't have an example here, but let's see. Like, I wish this would move. Yeah, there we go. So for O2, sometimes in the chart, they might include like oxygen with a triple bond between another oxygen, just to kind of throw you off. So it is good to review Lewis structures, how to draw the best Lewis structure and which one to use. This one, I don't think they throw you off too much. There's a C single O versus C double bonded to an O. So that would be important for CO2, knowing which one of these to choose. So again, it's just good to review Lewis structures here so that you know what bonds ultimately are being broken or what bonds are being formed. Okay. So notice that the bond energy for a double bond between carbon and oxygen is greater than it is for a single bond between carbon and oxygen. So remember, double bonds are shorter and stronger than single bonds. That's why we see this average bond enthalpy difference between those two. More energy is released when a double bond is formed, and double bonds require more energy to break because, again, they are shorter and they are stronger. So they would take more energy to break and release more energy when they are formed because they are a stronger, tighter bond. Okay. So for doing this, again, we're finding the sum of the bond enthalpies of bonds broken minus the sum of bond enthalpies of bonds formed. So the bonds broken are going to be on the reactant side. The bonds formed are going to be on the product. So you can also think of it like reactants minus products, if that helps you kind of to remember that. For each of these, if I could go back a slide, there we go. Remember, this is for one CH bond being broken. But how many CH bonds are there in a CH4 molecule? There are 4 of them. So really, we're going to be breaking 4 of these bonds. So this average bond enthalpy that we have, we're going to have to end up multiplying by 4. And same thing for oxygen. We have 2 O2 molecules here. We don't just have 1. So we're going to have 2 of these bond enthalpies being broken. And then we'd have to consider that for H2O as well. So keep in mind the number of bonds that you're breaking is also going to affect this. So again, if we have the sum of bonds broken minus the sum of bond enthalpy of bonds formed, we're going to have 4 times the bond enthalpy of a CH bond, because again, there are 4 there, plus 2 times the bond enthalpy that's present in an O2 molecule, because again, there's 2 O2 molecules there. And then subtract, this is where we take into account the products, the bonds formed. I'm going to move my picture here so you can kind of see. There we go. We're going to have 2 times the bond enthalpy of a CO bond, because in CO2 we have C double bonded to O and C double bond to O, so there's 2 of them, plus 4 OH bond enthalpies. And that 4 comes because with the structure of water, we have an O bonded to an H and an O bonded to an H. Well, that same O bonded to another H. And then since there's 2 of them, we have to multiply that by 2. 2 times 2 is 4. So that's where all this comes in. Okay, so now that we have this structure set up, we can go ahead and put in the values for all of those bond enthalpies. So that's where we get this 413, 495, 799, and 467 if we look back at the chart. And then if we add these sums together, we're subtracting 2,642 kilojoules per mole minus 3,466 kilojoules per mole, and we come up with a enthalpy change of enthalpy of negative 824 kilojoules per mole. So again, these values aren't very accurate, but you still need to be able to do this for the AP exam. Average bond enthalpies do not take into account the difference in phases, so whether we had solid, liquid, or gaseous water, we didn't really take that into account here, which is why it's not so accurate. So the enthalpy value for the combustion of methane when water liquid is a product is negative 890.5 kilojoules, and the enthalpy value when we produce water gas is a product is negative 802.3 kilojoules. So the value we obtained is somewhere between those two values because, again, we didn't take into account what phase water was in, because those bond enthalpies for water isn't going to be the same in the liquid phase as it is in the gaseous phase. So again, this is just a general estimate, not a very accurate method. And here we have another example. Calculate the average bond energy in an H to H bond. So in this case, we're again given the chemical equation. We're given the delta H of the reaction as negative 572 kilojoules, but we're trying to figure out what the bond enthalpy of this bond in H2 is. So we're kind of working backwards here. And I'm going to move this because it's again in the way. Okay, so again, we have delta H equals the bond sum of bond enthalpies of bonds broken, or the reactants, minus the sum of bond enthalpies of the products, or bonds that are formed. So our delta H is going to be equal to 2 times the bond enthalpy of HH. This is what we're solving for ultimately, plus, here we only have one O2 molecule, so it's the bond enthalpy of one O to O double bond, and then subtracted 4, again, because in each water molecule we have 2 OH bonds, 4 times the bond enthalpy of an OH bond. So if we rearrange this equation, we can solve for this bond enthalpy of HH, since these are all of our knowns, basically. And then we can start to plug in values here. So here we just multiplied everything by -1, just to kind of make things look a little bit neater here. And here we are solving for it. So we plug in negative bond enthalpy of OO plus the bond enthalpy of water that is being formed minus the bond enthalpy of the overall reaction, which is again negative because we are adding the negative. Okay. So then when we finally plug that in, we get a result of 401 kilojoules per mole. If you did not flip those values back in this step, you would have gotten a negative value, but bond enthalpies are usually going to be positive because it takes energy to break the bonds. So that's why they're reported in positive. So we would want to get a positive answer. So way back here in this chart, we have all positive values. So you would want a positive bond enthalpy answer, which is why we flip the signs way back in that step. Okay. That kind of summarizes 6.7. I will be sure to post the 6.7 worksheet online if you don't already have it in your packet. So that's going to be part of the homework. It's going to be working on that. And let me know if you have any questions. We have 2 minutes. I can go ahead and show you my lizard because why not? I do have a leopard gecko named Rosalind. She's pretty neat. So, gotta get her out. It is daytime, so she is like asleep right now, but she's pretty sweet. Okay, here is Rosalind. Putting her big rock down. She's a leopard gecko. She's really sweet. She just kind of sleeps all day. She has a really fat tail. During the winter, she's not very active, and she doesn't eat very much. But I'm hoping she starts to eat soon because I do worry about her. But they do what's called brumation, which is kind of like hibernation, where they basically don't eat for the winter. But yeah, this is Rosalind. I got her in college. She's a very good lizard. And yeah, bye. Have a good day.